Hello, welcome to this live webinar. I am Cédric Bélanger, Product Marketing Manager of Optical Solution at Ansys. Today I received the Product Owner of HUD Solutions, Sébastien Bram, and I'm very pleased to welcome the CEO of Surrey NanoSystems, David Wong. First, BCast, Thomas.
Yes, good afternoon guys. So first, if you want to interact with us during this presentation, please don't hesitate. It's the goal of the live session. You can really interact and ask your question to David and Ansys team. So don't hesitate on the wall to ask your question on the right of your screen, but you can also use the activities tabs where there will be some activities today, including polls and include words. So yeah.
So they have to change.
Yeah, they have to change the tab.
Wall and they change to activities to be able to answer the different polls.
Exactly, that's it.
Okay.
Yeah.
Thank you, Thomas.
Thank you.
So first, a few words about Ansys. Ansys is a global leader in engineering simulation, addressing the disciplines of fluids, structures, thermal simulation, but also systems, and recently optics. Our involvement in every major industry segment has provided us with the application know-how to help you solve the toughest problems. And wherever you are across the globe, Ansys can support you with nearly 3,000 direct employees and over 2,000 certified channel partners. Of course, Ansys is aligned with the leader of each industry. And the optical solution of Ansys come from the recent acquisition of Optis. In 30 years of innovation, Optis has gone from optical simulation to sound simulation. Last year, Optis has been acquired by Ansys and becomes part of a multi-physics and pervasive simulation platform. The topic today is how to solve stray-light issues in HUD systems. So Seb, what's the agenda today?
Thank you, Cedric, and hello everyone. So as Cedric said, the agenda of today is to talk about stray-light issue. It's a very common issue in head-up display systems that happens on almost all head-up display projects. So today we will first see how to detect the critical sun direction that will create this issue. Then we will see how to simulate this issue, and then we will see how to solve it in a very efficient way using the Vantablack material. So first, how to detect the critical sun position. So for that, I propose you to directly go into the CAD software. So here I have an example of a simple head-up display system. So as it's only for demo purpose, it's quite simple. If we have a look inside the housing box, we see that we have the mirrors, we have the picture generation unit, we have the housing box, the baffle, and the bezel. So a basic head-up display unit. If we have a look to the HOA simulation, so if you don't know this kind of simulation, you can review the previous webinar. We already talked about this kind of simulation. So this heads-up display optical analysis simulation shows that the picture generation unit will create a virtual image here, visible from this eye box. So on my data, I put an axis system on my virtual image that I will use later, and also an axis system on the intersection of the optical axis and the inner surface of the windshield that I also will use later. So the goal here of the first simulation we will do is to detect the critical sun position. So for that, we will emit light from the eye box and collect the light all around the environment. So first, we will define sources in the eye box. Up. Oops. So here I have a sources. I will collimate the source to sound the rays in the interesting part, the head-up display system. I don't care about the flux and the spectrum because for now, all what I want is to detect the light path that connect the eye box to the environment. So for now, I just want to sound rays to have this connection. And to collect these rays, I will create an intensity sensor here. Up. So like that. So this way, I will just use a conoscopic sensor and cover more space. I can increase the sampling of the sensor to have a better resolution. So now all the rays can be sent from the iBox, will be propagated into the system, reflect on all the part of the system, and then be collected by the sensor. So from that, I will create a simulation here, a direct simulation, where I will add the source, the sensor, and the geometry. So on the geometry part, I will add the picture generation unit, the windshield. I can add the iBox also. I will add the housing parts, as it's mainly the housing part that will create the Stralight issue with the mirrors. So I will also add the mirrors. And I can add other elements here. For example, I will add the dashboard. I will increase the number of rays I send. I will also activate the light expert mode because I will need this mode to visualize the rays directly in the 3D view of the CAD software, to visualize all the light paths that connect the environment to my iBox. And also here it's linked to the data I have. Here on my windshield I have two surfaces that represent my windshield, but I want to consider my windshield as a body. So I need to activate the volume optical properties on surface of the simulation, so the VOP, volume optical properties on surface. So from now my simulation is correctly set. I already applied the material to the geometry. So here if we have a look up on the buffer, for example, I already have a material with speos properties already applied. So here we can see that we already apply a black plastic that have about 6% reflective part. So from that, I will run the simulation. And during the simulation, all the rays will be sent from the iBox, will propagate into the system, reflect on all the geometry I set, also the mirrors and also the housing. And then I will collect back the rays on my intensity sensor, and it will create some hot spot on my intensity sensor where I know that it exists on this hotspot, a light path that connects this hotspot to my box and that can carry a lot of light, I would say. So here's the result of the simulation. I will just hide the sensor and the section here. Okay. So here I have the different critical sun position. So we can see in red the very critical sun position, in blue the non-critical sun position. From that, because I activated the light expert in the simulation, I can reopen the result and I can visualize in the 3D view the light path that connects one specific sun position to my iBox. So here, for example,
we do have some. How do you currently solve Stralights? We do have some words. They use CAD, physical prototypes, ray tracing, and simulations.
Okay. Okay. So here, to visualize the rays that link the environment to the iBox, we just analyze a part of the result. So it can be this part, for example, to know the light path that the ray take to create this spot here. And we will analyze this area right here. I will reduce the number of rays displayed to visualize more correctly the light path. I will also activate the section here. So from this hotspot, from this sun direction, what we see is that the light goes through the windshield, then hits the top of the freeform mirror, hits the bezel, and then hits the windshield, and then go back to the iBox. So from this critical sun position, some rays go to the iBox and can create Stralight. So I will extract these rays here, clicking this button. Here, okay, okay. So here it converts my light path into geometry. So now I have a line that I can use as a critical sun direction. So from all this line, I will extract one specific line. Up here. sorry. So a point here, and for the direction I will choose one of these directions. All these directions are almost collinear. And I will use the infinite ray. I will just isolate this ray here, so I can delete all the other geometry, so we have a more clear view on the 3D view. And here this ray correctly go on the direction we analyzed, of course. So this way we saw how to detect the critical sun position. So here it's an example also on how to extract one specific critical sun direction. Of course, in the real use case, you need all the geometry of your heads-up display, and you also need to analyze all the critical sun position. From the sun position we extract, we will simulate the issue. So from that, it's very simple. Now we have all the elements to do the simulation. So as we have now the critical sun direction, we will just create a sun on this direction.
When you say simulate, you will qualify the issue.
Yeah, we will experiment it as on the real car, in fact. So I will use for that the environment, the ambient source. It's not a product. I need to be on a product context to create a Speos element. So I will create an environment, ambient source, sorry, a natural light, and here I need the zenith of the sun. And here, for the sun direction, I can use directly the line I created here. I will click OK, and now I have a sun in this direction. I need a sensor to visualize the result as the real driver. I will use this one, the radian sensor. And I will use the axis system I placed on the virtual image to create it. I want to observe this image from the iBox. So here I will say that I want to observe it from the iBox. I will increase slightly the size of the sensor. And I will click OK. So now I have my source, my sensor. I could add also an environment source if I want to visualize my heads-up display and the stralight issue in the environment. And from that, I can create a simulation where my source will be the sun, so the ambient source. My geometry will be the geometry of my previous simulation. I can also add some other geometry, the HUD, the steering wheel if I want. And my sensor will be the one I just created. And also, for this kind of simulation, I need a lot of rays, so also lot of computation time. So it's why I won't run this simulation in live. But I will show you the results. So here with this material, a black plastic that reflects 6% of the light, we obtain this kind of result. So we clearly see the heads-up display. We see also the environment, but we also have this big issue, so the stralight issue, that is totally in the field of view of the driver. So now, up. So after experimenting this issue, we can propose a solution to solve it and to present the Vantablack, a material that can solve this issue. I will let the hand to David to present the Vantablack.
Sebastian. Can you hear me okay? I'm getting quite a lot of reflection.
We can hear you.
Excellent. Yeah, good. So we just heard from Sebastian how Speos can detect and help us resolve issues with stray light. And if it's not been possible to avoid those issues in the initial design, Speos has helped identify precisely what critical angles exist and how they might be addressed through either addition of baffles, change to the mechanical design, or, as is commonly done, the use of black coatings to absorb any stray light. Now, the designer has these different options available to him, but often they're quite limited. So volume in a windshield head-up display with the unit enclosed in front of the driver generally means there isn't very much more space, so additional baffles cannot be added. Redesign is always an option, but that can be expensive and time consuming. So black coatings are often selected, and they have to do a number of particular things. We've already heard about the importance of reflectance, and seen that with 6% reflectance, which is typical of the black plastics that are used, the issue is very much apparent. So achieving low reflectance, particularly at grazing incident angles, is hugely important. It's an automotive application, so clearly the coating has to be stable in that environment. Windshield HUDs can reach pretty high temperatures. The car has to go over bumps and rough roads, so there's some mechanical stability is also required, environmental stability. And by scalability, I mean there are probably 3 to 5 million HUDs, windshield HUDs being made today, and that number is going to increase. So we're going to have solutions that can be scaled up appropriately for the manufacturers. So moving on to the next slide, we can pick on each of those different elements. Vantablack is a coating that delivers all of those attributes that we've just discussed. And it does that by being a range of coatings that provide low density optical coatings that deliver extremely low reflectance, viewed from virtually any angle. And at a micro level, the coating is pretty rough. And consequently, its reflectance is effectively Lambertian. The low density coating, it differs from a paint in that it is not a dense film. And consequently, it's anchored to the substrate in many different places, and that allows it to flex and to be virtually immune from any thermal mismatches, and be able to take levels of stress, thermal stress and mechanical stress that you would not achieve with a dense paint. As the structure has this low density, it's very open, and it can be made even more open so that light that is incident upon it is reflected internally before it is absorbed by the absorbing elements. And that's what gives us this fantastic ability to absorb virtually all of the incident stray light. Now, I have mentioned a couple of times that this is a structure. It's not a dense film like a paint. So it won't withstand the sorts of physical abrasion that a conventional paint will withstand. And that's why we only use it in applications where it is protected in use.
We lose the sound? No?
Do you have me back?
No.
Yeah, no, it's okay.
Good. Yeah, get a lot of reflections. Sorry about that. So the reflectance characteristic, as we mentioned, you have to have low reflectance, but not just low reflectance when you're looking at the coating from near normal incidents. It has to deliver that reflectance when there's grazing angles involved as well. And you saw that very clearly illustrated in Sebastian's simulation a little earlier. And what you can see here is a graph of the bidirectional reflectance distribution function for Vantablack. And this shows, even with a 70-degree angle of incidence from the illumination source, the reflectance of the material is very low. Actually, it's less than 0.5% across the entire range. And that's what gives us the ability to suppress stray light and to eliminate those issues that we saw of artifacts that impact adversely on the picture quality and hence the quality of the device. And because this is a coating, it can be applied to multiple surfaces, including those which are commonly used in head-up display manufacture. Its retrofitting can help us deal with those issues. So rather than show you a graph, we've got a little video here that shows grazing angle performance for a paint that's typically used, flocking or baffle foam, and Vantablack. And that'll loop round again. This is a mask. It's a complex 3D shape. It's been sprayed with Vantablack. And you can see as it comes around, and you start to look at the thing directly, you lose all sense of three-dimensionality. Right? And this is that critical capability for retaining a very low reflectance, even at grazing angles.
David, we have a question, I think, regarding the... Thomas, you asked the question, or?
Yes, I do have a question. So, how does the reflectance compare with the standard matte black paints?
Yeah, the conventional black paints have reflectances of anywhere between 3% and 5%, but at near normal incidence. If you increase the angle of incidence up to the 70 degrees shown here, then you'll be approaching 10% or more.
Okay, thank you.
So, we've talked about reflectance being critically important, but there are a number of other issues which will weigh on the mind of any designer doing this. Environmental stability, critically important. Vantablack was originally developed for use in satellite-borne Earth observation equipment. So it has to be able to withstand the shock and vibration that is concomitant with launch, and be able to survive the severe atmospheres that we find, or lack of atmosphere, out in space. That means extremes of temperature and rapid changes in temperature and the shock and vibration that would happen. And in these types of applications, the material has to stay very, very firmly anchored to its substrate, because clearly we cannot have particle fallout that would then cause issues with any optics, because clearly this cannot be brought back to be repaired. Because these absorbers are made primarily of carbon, and they are very open structures, very low density, there's no contribution to fogging. So in terms of space measurements, when we look at total mass loss and things like that, we cannot measure any, and consequently Vantablack coatings do not contribute to fogging when used in these types of applications. And also, in order to make sure that its performance is maintained over its working life, the coating has to stay super hydrophobic. That's critically important through life, because if the coating takes on water, then generally its reflectance will increase, and hence its performance will be diminished. So another short video just to show you how this works. This is aluminium coated with some Vantablack being dipped directly into liquid nitrogen. Because of that open structure with multiple anchor points, you can see there is no thermal mismatch delamination of the coating, and it can be placed directly onto a hot plate at 300 degrees. And you can do this all the time with no degradation of optical or mechanical performance. And similarly, I think there's a little bit more
David.
there on hydrophobicity.
First, David, I have a question.
Mm-hmm.
Where has the coating been applied on the microsatellite?
Yeah, so on the microsatellite, you can see that is a communications satellite, and it uses a star tracker baffle. So you see those things sticking out at the front. They're used to look at a map of the stars in order to position the satellite. Now, of course, looking at a map of the stars from space sounds easy, but you have the sun in the way, which generates a huge amount of stray light, which causes contamination of the signal. So Vantablack is used in there in order to reject that stray light and allow the satellite to be positioned.
Okay. There is another question regarding the temperature?
Yes, there is another one. So can I apply the coating myself, and do I need any special equipment?
The Vantablack is made up of a range of different coatings, ranging from the ultimate sort of performance down at much less than 0.2% reflectance up to around 1%. Those that have the higher reflectances can potentially be applied directly by customers and users. There's a significant amount of capital equipment and expertise required to develop and deposit the the coatings which deliver the very best performance at less than 0.2% reflectance in the visible spectrum.
Thank you, David.
So I think if we go back to that other slide, Sebastian, I think there was the demonstration of hydrophobicity, if my memory serves.
Sorry?
It was the hydrophobic coating demonstration on that video. It didn't play. So we just roll forward in that. There you go. So this is Vantablack S-Viz, again on an aluminium disc. It's super hydrophobic, so if you put it in a little bowl of water like this, it will float. Surface tension is so high. You can force it under the water, and you can see that the water really doesn't like it, and it doesn't like the water. Take it out, and there you go. So a level of hydrophobicity that is really ideal for these types of applications. And as a space qualified material with legacy, you expect that it would be able to withstand severe shock and vibration, and it would do that without generating any particle fallout, which would otherwise obscure sensitive optics. But not only does it have to do that, it has to be suitable for use across a range of different materials, ranging from the alloys which are commonly used in space applications, but also onto plastics that are used in automotive manufacture, particularly glass-filled polycarbonates and cast aluminiums with magnesium content and things like that. And so that's been demonstrated. Again, we can achieve very high levels of shock and vibration resilience. You can see that here. You need a big armature on a shaker to deliver the types of accelerations that are required for space testing. And here, similar thing with a beam that resonates at 400 hertz that can be tuned to do different things. That demonstrates how Vantablack is really very easily capable of withstanding the sorts of shock and vibration for space launch. Makes it ideally suited to automotive application as well. Finally, just to talk a little bit about scale and scaling. Some of you may have seen at the beginning of last year, we did a 3,000 meter squared building at the Korean Olympics for one of the sponsor companies. You can see there a big building. It's about 3,000 meters squared. It was coated in one of our Vantablack products, and you can see there's a 3D star field there. Each of those lights is on the end of a 2 or 3 meter long rod, but you can't see that because it's all coated in Vantablack, and you get that really interesting effect.
Impressive. You went there, David, to see?
No, I didn't actually get it. It was too cold for me. So some of my colleagues were there getting very, very cold.
Okay.
And but Vantablack doesn't mind the cold.
Yeah.
So we can apply it to the 3D shapes. Can do it at really large scale. And because these materials are very, very low density, actually there's not a whole lot of material there. So in terms of end of life disposal burden, that there isn't so much to see. And there's one more short video on there which shows you a little bit of what happens with the way in which we can automate the spraying processes to suit different types of products, and how the post-processing is conducted where we wish to achieve the ultimate level of blackness using Vantablack coatings can get up to a reasonable scale. Thank you.
Thank you, David, for this introduction and the description of all the characteristics of the Vantablack material. So now we will use this material to solve the Strolight issue. So I propose you to go back in the CAD software. So here, I just remember we did the simulation that simulates the issue to visualize the issue like the driver will perceive it on the real car. So now what we will do, we will go on the Optis site and the Optis library, the Ansys Optis library. Here you just need to connect. You go on library, and from the library you can download the Vantablack materials that then you can use directly in a space simulation. So here you have the Vantablack material. You will download it. up. Then you will extract it. So on the folder I extracted, I have the datasheet of the Vantablack to have more information, characteristics, and also contacts. And I have the BSDF that can I use directly in Speos. So it's what we will do right now. We'll go back in Speos, and on the part that creates the Straylight issue, so here we will apply it on the buffer and the housing bottom. We'll just apply the Vantablack materials here. We'll use the Vantablack material, open. So here I have a warning because it's the first time I use this material. Speos asked me if I want to copy the material into the Speos input folder in order to have all the dependency of my project in only one folder. It's way easier when you want to share the project then. So I will say yes. And here you can see that the Vantablack material has been applied and from the Speos input folder. I will also apply the Vantablack material here to avoid any Straylight issue due to this part also. And from that now, I can run again my simulation to see if I still have the issue or if the Vantablack correct the issue. So it's a simulation with a lot of rays that take a lot of time, so I won't again run this simulation during this webinar, but I will show you the results. So you can see here the result. So it's the exact same simulation than previously, except we apply the Vantablack, and you can see that the issue is totally invisible. There is no more Straylight. We can go deeper and really look at the difference between the classic materials, classic black plastic. If we use the virtual lighting controller, we can disable the contribution of the display source that represent my picture generation unit, disable the contribution of the environment to really concentrate on the issue produced by the sun. Here the Straylight. So here you can see the Straylight, and here you have the value of the luminance here, so it's quite a high luminance. And if I look on, if I do the same on this simulation, so I will remove the contribution of the picture generation unit and of the environment, and I will have a very low luminance, so the issue is totally corrected and totally invisible with the environment and the luminance of the environment. So it's a very efficiency solution for the Straylight.
That's quite impressive.
Yeah, yeah.
How Speos can be used in modeling optical performance and hopefully avoiding these sorts of issues if it's used early enough. However, if you do find that there is an issue, Speos provides the designer with a suite of tools that they can use to identify those specific issues, and also allows them to home in on how they can be solved using a material such as Vantablack, which is entirely a retrofit solution.
Yeah.
Yeah, let's get kind of the wrap up. Yeah, it's. I think we know now how to detect the Straylight issues in the HUD system, but it's globally in an
of course the technique can be
system.
Apply.
Then how to qualify, how to experience, and then the best way to solve it using these innovative materials, the Vantablack. I have a question. How do you meet each other? Why? How do you contact? You contact David, or David contact you?
So yeah, it's kind of. In fact, the Straylight issue happen of lot of projects. So it's a really an issue that happen too much, I would say, and we need an efficient way to correct it. So it can be anticipated in some cases very early in the process, and the heads-up display box can be designed to avoid that, but due to the lack of space and also due to the lack that you can't put pieces into the optical volume, otherwise you will create a shadow on your heads-up display. You need a very absorptive material, and it's why the Vantablack is perfect for that. So it's kind of a very great solution.
Okay.
Yeah, and just to add to that, we found that Speos was able to accurately show what users were really experiencing. And this was a very easy means to demonstrate that there was a solution by the use of a material that was sufficiently absorbing. And I think that's been a really useful process, both for the device designers and makers and also for us.
Yes, I have a question, David, for you. You mentioned the satellite. What are the other use cases?
They vary.
For
It's used for light suppression in DSLR lenses. It's used in calibration sources and systems for terrestrial applications, and in a whole host of scientific instruments, microscopy, spectroscopy, and anything where a light source is used.
Okay.
It's a lot of application, I guess.
Okay. I have it's more a remark than a question from Marine Barret. She asked me, is the Vantablack is the new black?
I'd like to say it's the blackest black. So yeah.
Okay.
Well, is there any more
Any other
questions?
Don't hesitate to ask your
Thomas?
question. And even after the webinar, if you have still question, you can answer. You can ask us the question. We'll provide contacts just after.
So no, there is no more question yet.
Okay.
Just the result of the poll. So how important is Streetlight in your current project? So 67% say it's important for them, and 33% of the people say it's very important.
So it's very common and very
as
very
the
important
display is
challenge.
directly in the field of view of the driver, it's of course a passive quality issue, but also a safety issue. So,
so yeah, no more questions.
Okay.
Yeah. Well, thank you very much. Yeah, this webinar was the last of a very
Sorry.
a series of 5 we have delivered last year and
About heads-up
starting
display.
last year in June. So you can access freely the recordings on the Ansys YouTube channel, the playlist Head-Up Display Solutions. You can also have more information through the recording of the webinar on demand. What's new in Ansys Speos? So you will see what's new in the 2019 R1 version release that is available on demand, and you can, of course, you will have a lot of questions after watching this recording. So you can contact Sebastian here, but you can contact also David, Steve, or Michael from Surrey NanoSystems. You will find more information on their website too.
You can see the replay of the webinar on the YouTube channel.
Yeah.
Yes.
On the Ansys YouTube channel, you can see the replay of the webinar and all other videos we have about head-up display on the head-up display solution playlist.
So it's the end. On behalf of Ansys, we wish you a brilliant day.
Yeah.
Talk to you.
Thank you very
very
much.
soon.
Bye.
Bye-bye.
Bye-bye.
Bye.